Good morning students. Once again welcome back to session 9 of Banach spaces class. So in the last class you have studied what's meant by an Hanbanaki theorem. The Hanbanaki theorem states if M is a linear subspace of a nonlinear space X and if F is a functional defined on the linear space M, that means F belongs to M star, then the function f can be extended to a norm preserving functional f defined on the whole space X such that norm of f is equal to norm of f. This is also known as Anmanak extension theorem. Let us take up a few important corollaries to this theorem. Among them, the first corollary is, so the corollary states if X is a nonlinear space and x0 is a non-zero vector, in X, then there exists a functional f0 which belongs to x star such that f of x0 is norm of x0 and norm of f0 is 1. In particular, if x1 and x2 belongs to X such that x1 is not equal to x2, then there exists f belongs to x star such that f of x1 is not equal to f of x2. That means this f, linear functional f, separates the points of x. Okay. So now let us look at the proof. So I'll construct the linear subspace M generated by this non-zero vector x0. Okay. So then definitely M is a subspace of X generated by x0. And I define a mapping f from M to K such that f of alpha into x0 is alpha times norm of x0, because the element of M is generated by x0 means the elements of M is look like the multiples of x0. That means M contains set of all alpha into x0 where alpha is a scalar. Now we show T is linear. It's a functional means we need to show T is linear as well as it is continuous. First let T be linear. For this you take any two elements y1 and y2 in M. Then if y1 and y2 are in M, then how y1 looks? Y1 look like multiple of x0. This is alpha into x0, and y2 will look like beta into x0. Now consider let gamma and delta be scalars. Okay. And consider f of gamma into y1 plus delta into y2. This is equal to f of gamma into y1 means alpha into x0 and delta plus delta into y2 means beta into x0. So this is equal to f of gamma alpha plus delta beta into x0. So then by definition of f, this is equal to gamma alpha plus delta beta into norm of x0. That's equal to gamma alpha into norm of x0 plus delta beta into norm of x0. This is equal to gamma into alpha into norm of x0. I will group this, and delta into beta into norm of x0. We can always group like this. So this is equal to gamma into, what is this? Alpha into norm of x0 can be written as f of alpha into x0 plus delta into f of beta into x0. This is equal to gamma into f of alpha into x0 is y1 plus delta into f of y2. Thus we have shown that f of gamma y1 plus delta y2 as gamma into f of y1 plus delta into f of y2. Therefore f is a linear. Next we show that f is continuous. F is continuous means, say you take some element, say y belongs to M. That means y is equal to alpha into x0 belongs to M. Then what will happen? Norm of y is norm of alpha into x0. That we can write it as mod of alpha into norm of x0. Now mod of f of y is what? That's equal to mod of f of alpha into x0. That's equal to mod of f of alpha into x0 can be written as, this is equal to mod of alpha into norm of x0. So mod of alpha into norm of x0. But according to this, mod of alpha into norm of x0 is norm of y. So I written norm of y. But norm of y is less than or equal to 2 times norm of y. And definitely norm is, this is a fixed thing. So therefore mod of f of y is less than or equal to 2 times mod of 2 times into norm of y means what? You can say f is bounded. So f is bounded and hence continuous, because every bounded function is continuous in a non-linear space. Therefore f is linear, we have shown. Now f is continuous, therefore f is a continuous linear functional on M. Continuous linear functional on M. Further, what will happen? Norm of f is equal to, norm of f is by definition of a norm, supremum of f of y, mod of f of y, where y belongs to M, norm of y is less than or equal to 1. This is by definition. This is equal to supremum of mod of f of y according to our in the above steps. We have shown that mod of f of y is norm of y such that y belongs to M, norm of y is less than or equal to 1. So it is the set of norm of, so it is the set of supremum of norm of y, where y belongs to M, norm of y is less than or equal to 1 means what is the maximum value here is? It is 1. Therefore this is equal to 1 means norm of f is equal to 1. So therefore norm of f is 1. Also f of x naught is alpha into x naught is alpha times norm of x naught. So f of x naught is equal to what? Simply norm of x naught. Here we have taken alpha is equal to 1. Thus we have a linear functional. Thus we have a linear functional f from M to K means f belongs to M star such that f of x naught is equal to norm of x naught and norm of f is equal to 1, means the conditions of the required corollary being proved for the subspace M. Okay, then by Hanbanaki theorem, this function which defined on M can be extended to a norm preserving functional f naught which belongs to x star means which defined on the whole space x such that f naught of x is equal to f of x, but f of x is norm of x, so f naught of x is equal to norm of x, f naught of x is equal to norm of x, and norm of f naught is equal to which is norm of f, therefore norm of f naught is also 1. Thus we have proved the required result. Okay, the next condition is, so particularly suppose x and y belongs to x such that x is not equal to y. If x is not equal to y, then what will happen? X minus y is a non-zero vector. Then again by the above corollary what will happen? So if x minus y is a non-zero vector, then there exists a functional f belongs to x star such that f of x is norm of x. So f of x minus y is norm of x minus y. So since x is not equal to y, x minus y cannot be 0, therefore norm of a non-zero quantity is also non-zero. So this implies f of x minus f of y is non-zero. This implies f of x, since f is linear, we already shown f is linear, so f of x is equal to, f of x is not equal to f of y, means this f separates the points of x. Okay, separates the points of x. Next, let us take up the second corollary. Okay, corollary 2 says if M is a closed linear subspace of a non-linear space X, and if x naught is a non-zero vector which doesn't belongs to M, means which belongs to X, which doesn't belongs to M, then there exists a functional f naught belongs to x star such that f naught of M is 0 and f naught of x naught is not equal to 0. Okay. So now, since M is a closed linear subspace of a non-linear space X, you know that X by M is also a, we can construct a quotient space. That quotient space X by M is also a non-linear space with respect to the norm of a coset defined by norm of x plus M is equal to what? We already studied infimum of norm of x plus M, where M belongs to M and x is an element of x. And x naught is not an element of M implies x naught plus M is not a 0 element of x by M, that is 0 element of x by M is what? M. Therefore x naught plus M is not equal to M. Then therefore x naught plus M is a non-zero element of x by M. Then by corollary 1 what will happen? If x naught plus M is a non-zero element of x by M, then by corollary 1 there exists a functional f belongs to the x by m star means there exists a function f on x by m such that f of x naught plus m is equal to norm of x naught plus m and norm of f is equal to 1. Okay. Now I'll define a map T from x to x by m. I'll define a map T from x to x by m such that T of x is equal to what? The element x plus m, which is in x by m. Okay. Clearly we already shown that this type of mappings from the space to its quotient spaces is always linear as well as continuous. Therefore T is a continuous linear transformation from x into x by m. Okay. Now T is a linear map from x to x by m and f from x by m to k, this is always true. So f from x by m to k is also continuous linear map. Therefore the composite of these two, that is f, if I denote it by f naught, that's equal to f of t from where to where? This is from x to x by m and this is from x by m to k means, so f of t is a mapping from x to k defined by f naught of x is equal to what? F of t of x. This is equal to f of t of x. Okay. For every x belongs to x is a continuous linear map because f naught is a composition of two continuous linear map. Therefore f naught is also linear. That means f naught belongs to continuous linear map means what? F naught belongs to x star. So we have proved one condition. Say we have shown the existence of the continuous linear map on x or the functional which belongs to x star. Next you take, now if m belongs to m, then what will happen? F naught of m is equal to, f naught means f of t of m. This is f of t of m. F of t of m is what? M plus m. Now since m belongs to m plus m is m itself, therefore f of m is 0. But f of m is equal to f of m is f of m, but f of m is what? 0 because m is a 0 element of x by m. So the image of a 0 element is 0. This holds, thus f naught of m is equal to 0 for every m belongs to m implies what? F naught of m itself is 0. You call this as number 2. So in the one, we have shown the existence of a function on x, that is f naught belongs to x star, and here we have shown f naught of m is equal to 0. F naught of m is equal to 0. Let's prove the third condition. So the third condition is what? So we will take f naught of x naught. F naught of x naught is what? F of t of x naught. This is equal to f of t of x naught. So this is equal to f of t of x naught is what? Again x naught plus m. But f of x naught plus m is what? Norm of x naught plus m, which is non-zero, which is definitely norm of in element. This is a x naught plus m is a non-zero element because x naught doesn't belongs to m, so this is a non-zero element. Norm of a non-zero element is non-zero, so this is equal to not equal to 0, means f naught of x naught is not equal to 0. You call this as number 3. So now 1, 2 and 3 gives the required result because the theorem says there exists a functional f naught belongs to, the theorem requirement is there exists a function f naught belongs to x star that we have shown in 1, and f naught of m is 0 that we have shown in 2, and now we have shown f naught of x naught is not equal to 0 in 3. Thus we complete the proof of this corollary. Next let us take up the corollary 3. The corollary 3 says if x is again a non-linear space and suppose f of x is 0 for every f belongs to x star, then what will happen? If f of x is equal to 0 for every f belongs to x star implies x must be 0. X must be 0. Okay. Suppose x is not equal to 0. Then what will happen? Then by corollary 1, there exists a functional f belongs to x star such that f of x is equal to norm of x. But since x is not equal to 0, norm of x is also not equal to 0. This implies f of x is not equal to 0. But it is a contradiction because we have assumed that f of x is equal to 0 for every f in x star, which is a contradiction. This contradiction arises due to our assumption that x is non-zero, therefore x must be 0. Thus, f of x is equal to 0 for every f belongs to x star implies x must be 0. This is a simple corollary. Next, let us look at the corollary 4. The corollary 4 says if M is a closed linear subspace of a non-linear space X and let X naught doesn't belongs to M, means X naught is a non-zero vector which is not in M. And if D denotes the distance between x naught and M, then there exists a functional f naught belongs to x star such that f naught of M is 0, f naught of x naught is equal to 1 and norm of f naught is equal to 1 over d. Okay. So for this again, we will construct a subspace M naught using the subspace M and x naught, means M naught is the union of M and x naught. So any element in this space will look like x plus alpha into x naught, where x is an element of M and this is a multiple of x naught. Okay. Now definitely, if you consider this, M is definitely a linear subspace of X generated by which one? M and x naught. Therefore, M naught is a linear subspace of X generated by M and x naught. Okay. Then say we have given D is the distance between x naught and M. This is equal to what by definition of a distance? So infimum of norm of x naught minus x, where x belongs to M. But this is the smallest of these distances, means it is less than or equal to every element in this set. So the every element means less than or equal to norm of x naught minus x for every x belongs to M. You call this as number 1. Means D is less than or equal to norm of x1 minus x naught, or sorry, x naught minus x or x minus x naught. Okay. Also now x naught is not an element of M implies x naught is not equal to x for any x belongs to M. Okay, x naught will not coincides with x for any x belongs to M. This implies x naught minus x is not equal to 0 for every x belongs to M. This implies norm of x naught minus x is definitely, this is non-zero element, means norm of a non-zero element is always positive. So this is norm of x naught minus x is greater than 0 for every x belongs to M. X. Therefore, if norm of x naught minus x is greater than 0 means infimum of a positive numbers is also positive. Therefore, D is positive. Now, D is less than or equal to, according to one, D is less than or equal to norm of x naught minus x. Now, D is less than or equal to norm of x naught minus x means 1 over D is definitely greater than 1 by norm of x naught minus x. You call this as number 2. Now, I will define a functional. F from the subspace M naught to K by f of y. F of y means x plus alpha into x naught is equal to. So, it must be an element of K, scalar, means I will just take alpha. Okay. F of y is equal to f of x plus alpha into x naught, that is equal to alpha. I will call this as 3. Then what will happen according to this? Then f of x naught is equal to what? F of x is 0 here plus 1 times norm of x naught. This is simply alpha, means it is 1. Therefore, f of x naught is equal to 1. And also x belongs to M implies what? F of x is equal to f of x plus. So here I will take alpha is equal to 0. 0 into x naught. This is equal to what? 0. Therefore, f of x is equal to 0 for every x belongs to M implies what? F of M is also 0. Further, mod of f of y. Mod of f of y is what? Mod of alpha. This is equal to mod alpha into norm y by norm y. I multiply and divide it by norm of y. This is equal to mod of alpha into norm of y by this y. I can write it by norm of x plus alpha into x naught. So this is equal to mod of alpha into norm of y by, I will take mod of alpha outside. What will happen if I take mod of alpha outside? This becomes norm of x by alpha plus x naught. So mod of alpha I cancel on numerator and denominator. So this is norm of y by norm of x naught. I will write this as x naught minus x by alpha. Now x is an element of M. therefore what will happen? Minus x by also is an element of m. So this is less than or equal to norm of y into, but we are just now we know that by 2 1 by norm of x naught minus x for every is less than 1 by d for every x belongs to m. So I use that condition, therefore this is less than or equal to norm of y by d by 2. Okay, then I will take in the above I will take norm of f. Norm of f is what? Supremum of mod of f of y, where y belongs to m naught, norm of y is less than or equal to 1. So this is less than or equal to supremum of, just now we have shown mod of f of y is less than or equal to norm of y by d. So this is less than or equal to norm of y by d, where y belongs to m naught, norm of y is less than or equal to 1. So the maximum value is here what? It becomes 1, therefore the value is 1 by d. Therefore norm of f is equal to 1 by d. 1 by d. Thus, look here, we have proved that f is a linear functional on the subspace m naught such that f of x naught is 1, f of m is 0 and norm of f is equal to 1 by d. Means we have proved that there exists a function which satisfies the required condition in the theorem for the subspace m, for the subspace m naught. Therefore by Hanbanaki extension theorem or by Anmanak theorem, this f which is defined on m can be extended to a norm preserving functional on the whole space f naught, on the whole space x, such that f naught is equal to f on m naught and norm of f naught is equal to norm of f. Thus norm of f naught is equal to norm of f means norm of f naught is equal to norm of f, but norm of f is 1 by d, therefore norm of f naught is equal to 1 by d. Also f naught of x naught is equal to what? F of x naught. This is equal to 1. This implies f naught of x naught is equal to 1. Therefore, and f naught is equal to f on m naught. F naught coincides with f on m naught. So this implies f naught of m naught is equal to f of m naught. Okay. This implies f naught of m is equal to f of m, because m is contained in m naught. M is contained in, because m is contained in m naught. This implies f naught of m is equal to, f of m is 0 means f naught of m is equal to 0. Thus we have proved the condition for the linear space x. Okay. These are the few corollaries of Anmanak theorem. Okay, next let us take up the different concept. So we know from your analysis class that what is meant by a separable metric space or separable space. So when you say the norm-linear space x is said to be separable, so the norm-linear space x is said to be separable if it has a countable set which is everywhere dense in x. A norm-linear space x is said to be separable if it has a countable set which is everywhere dense in x, which is everywhere dense in x. Now we will prove a theorem based on this definition. A norm-linear space x is separable. A norm-linear space x is separable if its dual x star is separable. A norm-linear space x is separable if its dual x star is separable. Okay, that I have taken x be a norm-linear space such that whose conjugate space or dual space x star is separable. Okay, x star is separable means it has a countable dense subset. So I'll take S to be the set containing set of all f such that f belongs to x star and norm of f is equal to 1. Okay. Now since every subspace of a separable space is separable, S is separable because S is a subspace of x star which is assumed to be separable. Therefore S is separable. S is separable means what? By definition it has a countable dense subset. Let A containing the points or containing the vectors f1, f2, etc. fn and so on be a countable dense subset of S. Countable dense subset of S. Then each fn definitely belongs to S because this is a subset of S. Since each fn belongs to S, according to our definition of S, norm of Fn is equal to 1 for each n. Norm of Fn is equal to 1 for each n. But norm of Fn, according to definition, supremum of mod of Fn of x, where norm of x is equal to 1. So therefore what will happen? This must be equal to, this set must be equal to 1 because norm of Fn is 1. Now this set is equal to 1 means we have a sequence of elements here. So there exists some xn with norm of xn definitely is equal to 1. So there exists some xn with norm of xn is equal to 1 such that Fn of xn is greater than or equal to 1 by 2, because the supremum of all these values is 1 means definitely there exists some vector xn whose norm is 1 such that Fn of xn is definitely greater than of. Okay, such choice is always possible. Now I'll let M be the closed linear subspace of X generated by this vector, this sequence of vectors xn, or this vector xn. Okay, now we show that M is equal to X. We show that M is equal to X. Suppose, if possible, suppose that M is not equal to X. If possible, suppose that M is not equal to X. If M is not equal to X means what? There are some vectors in X which are not in M. I'll choose one such vector which is in X but not in M. Then by corollary to Hanbanaki theorem, what will happen? There exists a functional f belongs to x star such that norm of f is 1, f of x naught is not equal to 0 and f of m is 0. This we have proved. Now since norm of f is equal to 1, so norm of f is 1 means what? This f belongs to S. And since each xn belongs to M, and since each xn belongs to M, we have f of xn is equal to 0 for every n is equal to 1, 2, 3, because f by this one f of m is 0. Okay, now 1 by 2 less than Fn of what? Fn of xn we have shown in the beginning. 1 by 2 less than mod of Fn of xn. This is equal to Fn of xn minus f of xn plus f of xn. I add and subtract these two terms. So this is definitely less than or equal to Fn of xn minus f of xn plus mod of f of xn. So this is less than or equal to Fn minus f of xn plus f of xn is, because xn belongs to xn. So xn belongs to m means what? F of xn is 0. That I written it here. So this is less than or equal to norm of Fn minus f into norm of xn. But norm of xn is equal to what? 1. Therefore this is equal to Fn minus f. Means Fn minus f is what? Greater than or equal to 1 by 2. Fn minus f is greater than or equal to 1 by 2 for every n. Now by definition, now we have taken A to be dense set in S. Now A is dense set in S means what? Every point of A, every point of S is an adherent point of A. Okay, if A is dense in X, then every point of S is a adherent point of A, means the distance between the point of A and the point of X is very small. So for each open sphere, centered at arbitrary f belongs to S. For each open sphere centered at arbitrary function f belongs to S definitely contains a point of A. But the open sphere set of all f set at norm of f minus f less than of, because always norm of Fn minus f is greater than or equal to of. Therefore the open sphere as having set of all f set at f minus norm of f minus f is less than f, centered at where? Centered at big F belongs to S, contains no point of A. But this open sphere contains no point of A means, which is a contradiction, because we have assumed that A is dense in X, but according to this we will have a contradiction. Why this contradiction arises? Due to our assumption that M is not equal to X. Therefore M must be equal to X. Okay, M is equal to X. Now it then follows what? It then follows that the set of all linear combinations of xn's, set of all linear combinations of xn whose coefficients are rational numbers, because we need to have a countable set means what? We need to use the rationals. So we will have the set of all linear combination of xn's whose coefficients are rationals, or if X is complex nonlinear space, then we will have rational, real and imaginary parts constitute a countable set, a very dense in X. So we have a set of all linear combinations of xn's whose coefficients are rationals, or if X is complex, have rational, real and imaginary parts constitute a countable set, a very dense in X. Consequently, X is separable. We have a countable dense subset in X, therefore X is separable, because we have shown M is equal to X. So it is countable dense means what? M closure must be equal to X, right? Now we have assumed that the dual space of a nonlinear space is separable, and we have shown that the space X itself is separable. Now the question is, can the converse holds true? The converse part of the above result is what? The converse part of the above result is, if the space is separable, can its dual is separable? If the space is separable, then its dual space is separable. That is, dual space of a separable space need not be separable. The answer is, the dual space of a separable space need not be separable, because we know that L1 star is L infinity, means the dual of L1 is L infinity, and L1 is a separable space, but L infinity is not separable. Although L1 is separable, L infinity is not separable. In fact, LP is separable for every p less than or equal to for every p such that 1 less than or equal to p less than infinity, means LP is a separable, but L infinity is not separable. So now you have an assignment like, so we need to show the dual of L1 is L infinity 1, and the other is we need to show LP is separable but L infinity is not separable. You try these two results. Okay, that's all for this class. Thank you.